This video is going to work through your tracking test on Unit 1.5 equations up to balance symbol equations and Unit 1.6 the history of the periodic table. Question 1 refers to the history of the periodic table and talks about the works of Newlands and Mendeleev in the development of the periodic table. You are given 4 statements and asked to tick whether it was Newlands only, Mendeleev only, both Newlands and Mendeleev, or neither Newlands or Mendeleev. So the first statement is who stated the law of octaves, and that was Newlands only. So he stated the law of octaves and Mendeleev did not. Next statement was arranged elements in order of relative atomic mass. Well, Newlands did that, and Mendeleev also ordered his elements in order of relative atomic mass. So the one we're ticking there is both Newlands and Mendeleev. Next one is included noble gases. The noble gases were only introduced on the modern periodic table. That wasn't even on Mendeleev's periodic table. So if you think it was Newlands came first with the law of octaves, Mendeleev developed it further, and then you have the modern periodic table. But Mendeleev did not even have the noble gases. They weren't discovered at that time. So this answer is neither Newlands nor Mendeleev. They were only introduced on the modern periodic table. And then finally, left gaps for undiscovered elements. That was the work of Mendeleev only. Newlands did not leave gaps for undiscovered elements, but Mendeleev did. Question 2 again refers to the history of the periodic table, and this time we're comparing essentially Mendeleev's periodic table with the modern periodic table. So the first part of the question asks you to outline 3 features of Mendeleev's periodic table. And I want to underline that word features because what we need to be talking about here is features that were on his periodic table, not things that are missing. So a lot of people in this question referred to the fact that there were no noble gases, or there were no lanthanides and actinides, or things like that. But we're not looking for things that are missing from his periodic table. We're looking for features that are present. So things like no noble gases don't get a mark. While that is true, they're not a feature of Mendeleev's periodic table. They're essentially they're a feature that is missing. So that's not accepted as an answer. So just be really careful about how you phrase your answers. So what we were looking for with this was things like, how did he order them? What order did he put them? And he arranged them in order of increasing atomic mass. So if that's something you missed, then write that in. Arranged in order of increasing atomic mass. Okay, how did he group his elements, for example? And he grouped elements that had similar properties or similar reactivity. Another answer that would be accepted was the fact that he named the horizontal rows periods. So he placed elements with similar properties or reactivity in vertical columns called groups, and he named the horizontal rows periods. Another feature of Mendeleev's periodic table is that he left gaps for undiscovered elements. So there was gaps present on Mendeleev's periodic table, but you had to specify what those gaps were left for. The fact that he left gaps for undiscovered elements, ones that he thought would be discovered later on. So he left gaps for undiscovered elements. And then finally, one that is given as a separate answer is that not only did he leave gaps for undiscovered elements, but he predicted properties of the undiscovered elements. Again, you had to say that keyword, properties. Some people said that he predicted what the elements would be. He predicted their atomic number or mass number. No, he didn't do that specifically, but he predicted the properties of the undiscovered elements. And then finally, another feature of Mendeleev's periodic table is that while he arranged them in order of increasing atomic mass, just as we said back in point 1 here, he didn't maintain a strict order. He switched the mass order of some of the elements if it better suited their properties. So again, you need to be detailed about that. Some people talked about switching the elements, but that's not specific. He didn't switch the order of all of the elements, and you needed to talk about why. Why did he switch the order of some of the elements? And that was if it better suited their properties. So for the likes of iodine, he switched with tellurium because it better suited their properties. So you've got to be specific about that. Switch the mass order of some elements if it better suited their properties. Okay, so those are the key and main features of Mendeleev's periodic table. Again, you didn't get marks awarded for saying that there were things missing, like the noble gases, or for saying that there were less elements, because again, you're talking about things that are missing from Mendeleev's periodic table rather than features that were there. Next part of the question asks you to describe ways in which the modern periodic table differs, in other words, is different from the one proposed by Mendeleev. Best way to answer this question, and it was good to see that some of you did, is to say, well, Mendeleev's periodic table, for example, was ordered by atomic mass, but the modern periodic table is ordered by atomic number. But because it says describe 3 ways in which the modern periodic table is different, you can just simply refer to features of the modern periodic table that are different rather than compare. So if you had been asked to compare the two, you would have to say Mendeleev's is this, whereas the modern is this. But we're just going to outline features of the modern periodic table that are different from Mendeleev's. So first of all, as I've already mentioned, Mendeleev ordered his in order of increasing atomic mass. Ours is ordered by increasing atomic number. Then you can talk about the fact that noble gases are now included. So noble gases included. If we think about other specific groups or series that are present, you've got the lanthanides and the actinides are present. Where they weren't present on Mendeleev's periodic table. When you're referring to the transition metals, again, it must be specific that transition metals are now in a block. So Mendeleev had transition metals on his periodic table. He had zinc, he had iron, he had titanium and copper. They were all there, but they just weren't together in a block. So the transition metals are in a block. If you just said that the transition metals are there, you don't get a mark because that's not different from Mendeleev's periodic table. They were there in Mendeleev's periodic table, they just weren't together in a block. Other answers that were accepted were that there's a clear division between metals and non-metals. You know, the way we have the staircase or zigzag line that separates the metals and the non-metals. They accepted that some groups are now named, so the likes of your halogens or your alkali metals, they are actually given a name rather than just a number. In this particular mark scheme, the answer more elements was not credited, but what was accepted was the fact that there are no gaps in the periodic table. And if you had said there are no gaps because there are more elements, that's fine, but you had to say that there were no gaps. And again, that's not one of the best answers. So the most important ones are the fact that it's arranged in order of atomic number, the noble gases are included, but you did not get a mark if you just simply said more elements, but you would have got a mark if you said that there's no gaps now on the periodic table, and that is obviously different than Mendeleev's periodic table. So just when I marked yours, if you have a dot beside one of your answers, it's that yes, perhaps that is correct, but it wasn't accepted. You needed to go into more detail with that. Okay, so just be really careful what the question is asking you. Is it asking you for features? Is it asking you for things that were missing? Is it asking you for ways that it's different? Just read the question really carefully and make your answers really clear. Question 3 is asking you to write a balanced symbol equation for the reaction between fluorine and potassium bromide to produce potassium fluoride and bromine. In the exam, they may not give you the products, but we haven't studied this reaction yet, so the products haven't been given to you in this case. You don't have an awful lot of room there, so what I would suggest is that you take a blank page, particularly if you got this wrong and need to correct it, but even in the exam, take a blank page do your working out in the blank page and then write your final answer on the line. So what we need to write first of all with this is a word equation so that we can work underneath. So we're told that the reaction is between fluorine and potassium bromide. So those are my reactants. So they go on the left hand side of the equation. Fluorine plus potassium bromide react together to produce. So that means I put my arrow there. And my products are then potassium fluoride and bromine. So they go on the right hand side of the equation. So there's our word equation written, and that just is helpful, and we can work our way underneath that. So next thing I need to do is write my formula for each of these terms. And what I mean by that is taking each one of my reactants and each one of my products and converting it into formula. So the first thing I look at is fluorine. I know that fluorine is an element on the periodic table, so I have to ask myself, is it diatomic or is it not? If it's not diatomic, I simply write down the symbol of it. If it is, I need to include a little 2 after the symbol. So look at your periodic table. You should have fluorine highlighted. It is a diatomic element, so I need to write it as F2. Potassium bromide then is an ionic compound. It's an ionic compound, so I need to use swap and drop to get its formula. This is where a lot of people made mistakes. You've got to be so careful with this. Potassium bromide is just a simple swap and drop with 2 elements. So what we need to do is write down our symbols with their valencies. So potassium is in group 1. It has a symbol of K. Find it in the periodic table. Have your periodic table open in front of you now as we go through this. And then look to the top of the group. It's in group 1, so it has a valency of 1. Bromide, now notice this is not bromine, so it's not the element bromine anymore. It's bromide because it's part of a compound. So I no longer consider it as diatomic because it is part of a compound. So I simply write down the symbol, which is Br, and I look at the top of the group for the valency. A lot of people are using the valency of 2. I think they're thinking because it's diatomic. But if you look at the top of group 7 only need to gain 1 electron to get a full outer shell. So that's why they have a valency of 1. So it should just be Br with a valency of 1. When we swap and drop that then, we ignore our 1s, and so our formula should just be KBr. So don't overcomplicate that. You just write down your 2 symbols with their valencies and check the top of the group for the valency. It's nothing to do with the fact that bromine as an element is diatomic, because it's not diatomic as part of a formula, and we don't use that to get its valency. Potassium fluoride, then we need to do the same thing, swap and drop. So it's an ionic compound, so we need to use swap and drop. So again, we've got potassium with a valency of 1. Fluoride is just fluorine that's become a negative ion. And we look to the top of the group and it has a valency of 1. Swap and drop those and you get an answer of KF for the formula. And then finally, we've got bromine. And again, I know bromine is an element, it's on its own here. And I look to the periodic table, I'm asking myself, is it diatomic? And yes, it's highlighted, so it is diatomic. So I must write it as Br2 rather than just Br. So now I can write my equation again, but substituting the words for the formula. So I've got fluorine, which is F2, plus potassium bromide, which is KBr. An arrow, potassium fluoride, which is KF, plus bromine, which is Br2. So there's my equation, but I have one last thing to do, and that's to balance it. In order to balance it, I'm going to put boxes in front of my formula to remind me that I can only put numbers there. I can't change the formula at this stage. I can only put numbers in those boxes. So let's have a look at our elements. What I want to do first of all is list my elements, separating out everything. So I've got fluorine F, potassium K, and bromine Br. Copy this list in the same order on the right hand side, otherwise you can get mixed up. Next step is to count up your elements. So on the left I can see I've got 2 fluorines, 1 potassium and 1 bromine. On the right I have 1 fluorine, 1 potassium and 2 bromines. So you can see that my fluorine isn't balanced and my bromine isn't balanced. How do I get my fluorine balance? Well, I want 2 on the right hand side. So I'm going to put a 2 in this box to get me 2 there. Remembering that these numbers multiply the number within the formula by that number. So I've got 2 multiplied by 1, which is 2 fluorines. So I cross that out, I've got 2 fluorines. But I've also affected my potassiums as well, because that's part of this formula. I've got 2 multiplied by 1, which is 2 potassiums. So now my fluorine's fixed, but my potassium is now unbalanced and my bromine is still unbalanced. I'm going to look to the left hand side now. That's where I need more elements, or more atoms. And how am I going to get 2 potassiums in the left? Well, I'm going to put a 2 in this second box. That's affected my potassium and my bromine. Again, do your multiplication. With potassium, you've got 2 times 1, which is 2. And 2 times 1 bromine, which again is 2. And you can finally see your lists match and your equation is balanced. So then, once I've done all that working out, maybe on a spare page or in the back of my exam paper, I'm going to rewrite my final equation without the boxes. So it's F2 plus 2KBr, giving you 2KF plus BR2. Question 4 was a question regarding electronic configuration, how that would ultimately affect the formula of a compound when element Q reacts with element R. These are just made up symbols. I have drawn the electronic configuration out as a structure formation on the right hand side of the page here, just to help me visualise this, help me see this, but it's not totally necessary for this question. So you're told that Q has an electronic configuration of 2881. R has an electronic configuration of 2,6. And we're told importantly here that Q forms an ionic bond with R, so that's taking us back to unit 1.2. And we know that in ionic bonding we see the transfer of electrons from metal to non-metal. Okay, so part A, part 1 asks how many electrons are transferred from an atom of element Q when it bonds with element R. So we're having a look at atom Q here, and we're having to think how many electrons are transferred from this atom. Well, if you remember back to the bonding topic, what an atom wants to do when it bonds is to get a full outer shell. How does it do that? Well, you can see it has 1 electron in its outer shell, so it's going to lose that. It's going to transfer that to Q ultimately. It's only got 1 electron in its outer shell, so it can only lose 1. So the answer to this is that it has 1 electron to transfer to R. Part 2 then asks how many electrons does an atom of R need in order to become stable. We can see it's got 6 electrons in its outer shell. What does it need to become full? It needs a total of 8 electrons. It needs 8 electrons. It's currently got 6 in its outer shell, so it needs 2 more. Next part was write a formula using the symbols Q and R. So some people tried to find out what this was in the periodic table and use those symbols, but it says using the symbols Q and R. So we just stick with that for the compound formed when they bond ionically. Okay, so there's a couple of ways you can think of this. First of all, you might say, well, Q has 1 electron in its outer shell. So it's group 1. And all elements in group 1 have a valency of 1. Element R then is in group 6 because it has 6 electrons in its outer shell. And if you look to the top of group 6, they all have a valency of 2. And then you can simply do your swap and drop. And that would get you Q2R, because we ignore the 1s. So that's one way you can do it. Think about what would the valencies. And you can think about the valencies really mean, well, how many electrons is it going to lose or gain? Q is going to lose 1, R is going to gain 2. And that's where we get the valencies from. Or you can think about it logically, and some of you referred to this but got the wrong final formula. If we think about it, Q needs to lose 1, but R needs to gain 2. And therefore, if you think back to your ionic bonding explanations, we would be saying at this point, therefore 2 Qs are needed for every 1 R. So if we need 2 Qs for 1 R, how I would put that together in a formula is I need 2 Qs for every 1 R. Q2 for 1 R. So essentially Q2 R1, but then we ignore the 1. So that's where we get our working out for that. Question 5 was back to the history of the periodic table. You were given a section of Mendeleev's periodic table, which we will come back to in a second. It said, in what order did Mendeleev set out the elements? And that's in order of increasing atomic mass. So in order of increasing atomic mass or relative atomic mass was fine. They did not accept mass number. Okay, because mass number is specific to an isotope, if you remember from topic 1, atomic structure, but it must be atomic mass or relative atomic mass. So name the group of elements known today, which is not in Mendeleev's periodic table. This is where you've got to be careful. It says name the group. What is a group in the periodic table? A group is a vertical column. Okay, so that is a group, is a single vertical column. Okay, so a single vertical column is a group. Some people talked about the transition block of elements. Yes, that was not there on Mendeleev's periodic table, but a block is not a group, because it's, if you think about the transition block, it is multiple groups. It's 10 groups in total in that block. And the same with the lanthanide and the actinide series. They're not a group, they are a series across multiple groups. Okay, so the group of the periodic tables that we're looking for here are noble gases, because they are our final column, our final vertical column, so therefore they are a group. Suggest a reason why this group was not in Mendeleev's periodic table, and simply because they hadn't been discovered yet. Okay, so they had not been discovered. Next one, using the data leaflet and your knowledge, name one element that Mendeleev placed in the wrong position. A lot of people here were talking about iodine and tellurium, and those are ones he switched in order to better suit their properties, but that was not the wrong position. And in fact, now looking at our modern periodic table, that was the correct order to put them in, because now that we have them in order of atomic number, it fits. Tellurium comes before iodine, just as Mendeleev had switched. So that's not what we're looking for here. What we're looking for is basically ones that are mentioned in this table above and that are in the wrong position. So one that would be accepted is hydrogen. You can see that on our periodic table it's out on its own. That's because it doesn't fit well into group 1, because it is it's a non-metal, whereas all the other group 1 metals are alkali metals. So it doesn't fit well into group 1. However, some periodic tables do have it at the top of group 1, so it's probably not the best answer, but hydrogen would be accepted. If you look down group 1 as well, there you've got copper at the bottom, which you can see is now in the transition block in the modern periodic table. It's not in group 1. So you're basically comparing this little table here, this portion of Mendeleev's periodic table, and saying, well, what if this is in a different position than the modern periodic table? If you look at group 2, all is fine, beryllium, magnesium, calcium, but then you've got zinc at the bottom of group 2. Again, it's now in the transition block, so it's in the wrong place. Group 3 is fine, boron and aluminium. Group 4, carbon, silicon, fine. Titanium is not. Again, it's in the transition metal block, so it's in the wrong position. Group 5 then, you've got nitrogen and phosphorus, that's fine. Then you've got vanadium, but again that's in the transition metal block, so that is in the wrong position. AS is arsenic, is not in the wrong position, because essentially if you remove vanadium, then arsenic would be in the right place underneath phosphorus. So it does appear below phosphorus on the modern periodic table, so its position is fine, so it was not accepted. Look at group 6, oxygen, sulfur, they are fine, but chromium, that is a transition metal, so that should be in the transition metal block. It's in the wrong position. But then again, if you remove that, the next one in line would be selenium. The next one in group 6 would be selenium, so selenium is in a fine position. Then looking at group 7, you've got fluorine, chlorine, absolutely fine. Then you've got manganese. Again, that should be in the transition metal block, so that should not be there. And then finally, you've got bromine at the bottom there, which is fine in group 7. It belongs in group 7. Again, if you remove manganese, that would fit. And then you've got iron, cobalt and nickel. Again, those are fine where they are essentially now in our central block, in the transition block, but they are over there on their own and not in a group number. So those are fine there. So your best answers are the ones I've highlighted there: hydrogen, copper, zinc, titanium, vanadium, chromium or manganese. And then if we look at part C again, it says, just to highlight here, it says name one element that Mendeleev placed in the wrong position. So you must write the full name, not just the symbol. So some people were maybe writing Ti for titanium, but you should have written the full name for that titanium. So be careful if it asks you for the name or the symbol, because sometimes you're not given the mark if they have asked for the name and you just write the symbol, and then they sometimes do not give you the mark. I have in this case, but just be really careful with that. And then finally, in what order are the elements set out on the modern periodic table? They are set out in order of atomic number, increasing atomic number rather than atomic mass. So that's one of the key differences between the modern periodic table and Mendeleev's periodic table. So a lot of you got this right here, but then maybe didn't write that for question 2 in one of the key features or the key differences in the modern periodic table. So if you're asked a question like that, go back and then add that to your other answer. Moving on then to question 6 was simply to balance the equation which describes the reaction between sodium oxide and hydrochloric acid. So you've been given the formula, you don't need to do any work on that, any swap and drop or anything like that, just your balancing. So you can put your boxes in, or you can just simply remember that you can only put numbers in front of the formula. So let's make the list of our elements and we'll do our working out below. So you can see that you've got sodium, you've got oxygen, you've got hydrogen, and then you've got chlorine, it's Cl. Some people split that up into C and then I, but remember it's hydrochloric acid, so it's HCl. I know the font is maybe not the best here, but think about it practically, it's hydrochloric acid, so it will be HCl. Do the same on the right hand side, and you're best keeping them in the same order, and that allows you to compare. Now, next you count up your atoms on your left hand side, so you can see you've got 2 sodium, 1 oxygen, 1 hydrogen and 1 chlorine. And then on the right you've got 1 sodium, 1 oxygen, 2 hydrogens and 1 chlorine. So you can see our sodiums and our hydrogens are the ones that need fixed. So again, put your boxes in if you need to. I'll put them in temporarily here. Okay. And so if we look at, for example, sodium, how am I going to fix that on the right hand side? Well, I need to put a 2 here. Okay, so that has now affected my sodium and my chlorine because they're both part of that formula. It multiplies everything in the formula by that number. So I now have 2 sodiums and I have 2 chlorines. So I've fixed my sodiums, but I've created a problem with my chlorine, and hydrogen is still a problem. So I need 2 hydrogens, 2 chlorines on the left hand side. Well, how I get that is I'm going to put a 2 in front of my HCl. I've affected my hydrogens, my chlorines. I now have 2 times 1 hydrogen, which is 2. And 2 times 1 chlorine, which is also 2. And you can see my lists match, and so the equation is balanced. So either if you've put boxes in here, you'll need to rewrite your whole equation. I'm just going to rub out my boxes and rewrite my numbers in. So I had a 2 in front of my NaCl and a 2 in front of my HCl, and that's that equation balanced. Moving on then to question 7 again. Use the back or a spare piece of paper to do the working out of your formula if you need. So it says here that the products are potassium hydroxide and hydrogen. So for these questions, and I'll show you in the next example, you get a mark for what's on the left, a mark for what's on the right, and then a mark for balancing. But this one is a little different because you're asked to complete the equation. So you get a mark for each of the formula of your potassium hydroxide and your hydrogen. So potassium hydroxide, first of all, if I maybe scroll down to the bottom of the page just to do the working out of this. So potassium hydroxide, with this you have to remember that hydroxide is an example of your molecular ion, which is on the back of the periodic table. If I look at its formula on the back of the periodic table, make sure you have one open in front of you and you can look at this. Its formula is OH-. Okay, so we'll come back to that in a second. So potassium, first of all, potassium is K. It's in group 1, which all have a valency of 1. Hydroxide then, the first thing you want to write down is your formula. And remember that your formula is everything apart from the charge. I'll maybe circle that in a different colour. It's everything apart from the charge. So I write down OH, and I'm going to put that in brackets. If it's ever a molecular ion, you put the formula part of it, all the letters, the symbols and the numbers at the bottom. Hydroxide doesn't have any numbers at the bottom in this case. You put them in brackets. Okay, and that's because any number you swap down will apply to the whole molecular ion. Next, we use our charge for our valency. So our charge is minus or -1, so that means my valency is 1. So I don't include the minus sign anymore. There should never be a sign in your final formula. There should never be a sign in your final formula. So you can see I've just got ones here, so I swap and drop, and I'm just going to get K brackets OH. And then because there is no number after the brackets here, then I can remove my brackets. It's just KOH. Basically, if your valencies are the same when you're doing these swap and drops, you will not need brackets, because your valencies are going to cancel out, and then your brackets can be removed. So my formula for potassium hydroxide is KOH. So I'm going to write that in my equation up here. So I've got KOH is potassium, and then I also produce hydrogen. Okay, what I need to do is, well, hydrogen's an element. I need to check, is it diatomic? Look at your periodic table, it is diatomic. So I need to write it as H2. A lot of people lost marks there. So you got a mark for your potassium hydroxide formula, KOH, a mark for the hydrogen formula, H2, and then now we've got a balance our equation, and you get a mark for that. So list your elements. You've got potassium, hydrogen, oxygen, and do the same on the right hand side as well. Potassium, hydrogen, oxygen. Keep them in the same order. Count up your elements then. You've got 1 potassium, 2 hydrogens, 1 oxygen on the right. On the left. On the right hand side you have got 1 potassium. Hydrogens, be careful because you've got 1 here and 2 here, and that's a total of 3. So that's 3 hydrogens. And then you've got 1 oxygen on the right. So at the minute, my only atom that is unbalanced is hydrogen. I'm not going to fix this in one go, but remember we can only put whole numbers in front of the formula. I'm not going to put boxes in here because I don't have much space, but remember you can only put numbers in front of your formula. Ideally you would have this written out at the back with boxes in front. So I would ask myself at this point, well, what side do I need more hydrogens on? I need more on the left. How am I going to do that? Well, I'm going to do that by putting a 2 in front of my water. That's going to affect my hydrogens and my oxygens. So think about hydrogen now. You've got 2 times by 2, which is 4. And you've got 2 times by 1 oxygen, which is 2. So I haven't fixed my hydrogens yet, and I've created a problem with my oxygen. If I look at my oxygen, it's probably going to be easier to fix. So I've got 2 on the left and only 1 on the right. How am I going to get 2 on the right? Well, I'm going to put a 2 in front of the formula that contains oxygen. That's actually going to affect my potassiums, my hydrogens and my oxygens. And this is where I think some people started to go wrong. So be really careful with this. So potassiums, it's 2 times by 1, which is 2. With hydrogens, count up the whole right hand side again. You've got 2 times by 1 here, which is 2. But then you've also got these 2 here. So you add them on, and that's 2 plus 2, which is 4. So let me go over that again. It's 2 times by 1 here, which is 2, plus these 2, which is 4. So 4 hydrogens in total. Then we've got oxygens, and again we've got 2 times by 1, which is 2 oxygens. So my oxygens are fixed, my hydrogens are now fixed. Just got to fix my potassium, and I'm going to do that by putting a 2 in front of my K, which gives me 2 potassiums on the left hand side. So your final answer is 2K plus 2H2O gives you 2KOH plus H2. Lastly then on this page it says when sodium reacts with bromine it forms the compound sodium bromide. write a balanced symbol equation for this reaction. So again, let's do our working out below, and we're going to write our balanced symbol equation, or our word equation first of all. So it says when sodium reacts with bromine, so sodium plus bromine, it forms, so it's reacting with, and that's where my arrow comes in, it forms the compound sodium bromide. So that's going to be a product. So even if you wanted, you could start at the question saying when sodium reacts with bromine, okay, well that must be a reactant. Bromine must be a reactant. It forms the compound sodium bromide. That must be a product. So work out what your reactants or products are. Reactants go on the left, products go on the right. So again, I just as I've done before, I want to convert these terms, these reactants and products, to symbols. So sodium I know is an element. It's an element. So I want to check, is it diatomic? Look at your periodic table. You haven't highlighted it. It's not diatomic, so I simply write down the symbol. I don't write down its valency because it's not part of a compound. It's just an element. So I just write its symbol down, and it's not diatomic. Bromine then, it's an element. So I need to ask myself, is it diatomic? And in this case it is, so I must write it as Br2. Sodium bromide is an ionic compound, so I need to use swap and drop. Again, sodium is in group 1, so it has a valency of 1. Bromine is in group 7, so I write down Br, and it's in group 7, so it has a valency of 1. Not a valency of 2 because it's diatomic or anything like that, and it doesn't have a 2 on the end because it's diatomic. It's only diatomic when it is an element on its own. Can't cancel down those valencies at all, so it's just simply NaBr. So I rewrite my equations with boxes in front. I've got Na plus Br2 giving me NaBr. All I have to do now is balance. And this is quite a simple equation to balance. I've got sodium and bromine on the left and sodium and bromine on the right. How many sodiums do I have is 1. How many bromines do I have on the left is 2. How many sodiums do I have on the right is 1. And how many bromines on the right is 1. So I need another bromine on the right hand side. So I'm going to put a 2 in this box here. Put a 2 here. But that's affected my sodium and my bromine. So I've got 2 sodiums and 2 bromines now. So now I need 2 sodiums on the right hand side. So put a 2 in this box. And that gives me 2 sodiums. And my final answer is then 2Na plus Br2, giving you 2 NaBr. In these questions where you're given 3 marks for a balanced symbol equation, you get 1 mark for the left hand side. So that's if all of the formula on the left hand side are correct, you get a mark. If all of the formula on the right hand side of your arrow are correct, you get a mark. And then if you've got both of those marks, if the left hand side and the right hand side are correct, then you get an extra mark if your balancing is correct. But if your formula on your left or your right or both is wrong, then you can't get the balancing mark. You can only get that 3rd mark if your left hand side and right hand side is correct. So you'll notice on the marking I may have given you, for example, tick, tick, tick. That would mean the left hand side is right, the right hand side is correct, and the balancing is correct. If I gave you, for example, X, tick, X, then that means the formula, something in the formula on the left is incorrect. Your right hand side is correct, so you'll get 1 mark, but you then can't get the mark for balancing, so that's where the 3rd X is. So the first ticker X refers to the left hand side, the second ticker X refers to the right hand side, and the 3rd ticker X refers to the balancing. So again, if you're happy with your formula, try to get to the stage where you've got an equation written, because you could get 2 out of 3 of your marks even if it's not balanced. And if you're not sure what the formula on the right hand side is, then still write the formula on your left hand side, because you could still get 1 of the possible marks. Okay, and then finally question 8 was a simple formula question, but there was quite a few common mistakes made here. Key things that you you needed to know were definitions, and some of those referred back to atomic structure. So it said, from the box above, choose a cation with a charge of 2. And what you needed to remember is that cations are positively charged ions. Remembering also that an ion is a charged particle. So a charged particle, so it will either be positively charged or negatively charged. So a cation is a positively charged ion. So I'm looking for a positively charged ion that has a charge of 2. So essentially I'm looking for something with a charge of 2 plus. And what I can see in my table is that I've got Mg2 plus. So you had to remember that cation was positively charged ion. A molecular ion then is essentially an ion that is a molecule. So the likes of K plus and S2 minus and Cl minus, Mg2 plus and N3 minus and Al3 plus, those are just single atoms that have become charged by either losing or gaining electrons. So they're just simple ions, we would call them, and they're just a single atom that has become an ion. But if you think of a definition of a molecule that you learned way back in year 9, a molecule is a substance that contains 2 or more atoms chemically joined together. They can be the same or they can be different, but a molecule contains more than one atom. Okay, so if you want to put that in, a molecule contains more than one atom. So a molecule contains more than one atom, and so a molecular ion is simply a molecule that has become charged. So an ion, if it's a charged particle, and that word molecular refers to molecule, which means that it has more than one atom. So what I'm looking for here is a formula, a symbol of something that has more than one atom and that is charged. So there's 2 of them here in your table. You've got sulfate because you've got 1 sulfur, 4 oxygens and a charge, and you've got nitrate, 1 nitrogen and 3 oxygens, and it is charged. So those are our 2 molecular ions. So either answer was fine. NO3 minus / SO4 2 minus, either answer was fine. A symbol which is not an ion, well, if I go back to my definition here, an ion is a charged particle. So any of those ions or any of those particles that have a charge on them, they are ions. So the only one that does not have a charge is Na. And then finally the symbol for the nitrate ion, what you need to remember is that nitrate is, and again you learned this back in year 9, when it ends in 8, that means that there's oxygen present. So nitrate is nitrogen plus oxygen, nitrogen bonded with oxygen. If it was just simply N3 minus, that is what we would call a nitride ion. So IDE means it's just been the atom that has become an ion, but nitrate means there's nitrogen and oxygen. Also can be found in the back of the periodic table. If you check there, you can see that nitrate is NO3 minus. So that's the end of your test. So go back and look through questions that you didn't get right. Make sure that you've corrected them and maybe try them again without the answer in front of you, particularly for your balanced simple equations.